name is Pak Junsi, and I'll be presenting on distributed systems today. So my group includes myself, Winston, Ku Mingjin, and Ng Zheng Yu. So I'll start with the introduction. Modern computer systems generate a large volume of log data, including web server access logs, application error logs, and security audit trails. So these logs are essential for monitoring system behavior, identifying performance issues, and detecting potential security threats. So, however, as systems grow larger and more complex, processing logs on a single machine becomes slow and inefficient, especially when real-time analysis is needed. So that's why we chose to do log processing. So this is our motivation for log processing. We chose log processing because it's a real-world problem faced by most organizations today. Log data is naturally parallelizable, as each log entry can be processed independently. This makes it suitable for distributed platforms like Hadoop MapReduce, where data is split across multiple nodes and processed in a parallel. By combining distributed storage and parallel processing, the system can scale efficiently as log size increases.
For this slide, I'll be talking about use case. The use case we're going to use is Apache Web Access Log Analysis. Apache Web Server are widely used to host website, web application, and APIs, and they generate an access log entry for every HTTP request received. Each log entry records important information such as client IP address, the time of request, the requested URL, and the HTTP status code. In a high-traffic system, Apache server can generate thousands of log entries every second. Over time, this log file becomes very large. If we try to analyze this log using a single machine, the process becomes slow, resource-intensive, and inefficient, especially when analyzing log collected over several days or weeks. Therefore, the main problem we are solving is how to efficiently analyze large volume of Apache access log. In the next slide, I'm going to talk about what we analyze from the use case. From the Apache access log, we perform several important analyses that are commonly used in real-world systems. First, we identify the most requested URL to understand which content is accessed the most. Second, we analyze the most frequent client IP address to identify heavy user or potential automated traffic. Third, we examine the distribution of HTTP status codes such as 200, 404, and 500, which help detect broken links, configuration issue, or server-side error. This analysis helps system administrator and engineer monitor system performance, improve reliability, and detect abnormal behavior. In the next slide is why Hadoop MapReduce. The reason is Apache access logs are well suited for distributed processing because each log entry represents an independent event. This means the log can be split and processed in parallel across multiple machines. We use Hadoop MapReduce for this task during the map phase. Each log line is parsed and converted into key values such as URL will count of 1 or IP address will count of 1. During the MapReduce phase, these values are aggregated to produce final results such as total request count. MapReduce allows the system to scale easily by adding more workers nodes as log volume increase, making it an efficient and scalable solution for large-scale log analysis.
Our project assesses the challenge of exponential log growth that overwhelms single machine system. We select the Hadoop MapReduce framework because it is specially designed for parallelizable dataset like Apex asset logs. By using the Hadoop distributed file system (HDFS), we move away from traditional storage that copy data to a central processor. Instead, we send our processing logic directly to the data nodes, where the log blocks are stored. The concept of data locality is what allows our system to scale horizontally by simply adding more nodes as traffic increases. We developed the architecture of AWS EC2 using a total of 6 instances, 1 master node, and 5 slave nodes. The master node acts as the cluster brain, running the name node for metadata and the yarn resource manager for job scheduling. Before any configuration began, we established a strict security group policy. We enable TCP port 9x70 and x088 to allow us to monitor the HDFS and yarn web interface, ensuring we have full visibility into the cluster health for our browser. To synchronize this instance, we added the etc screw host file on every node, mapping private IPS to hostname so the node could communicate as a undefined cluster. We can standardize the environment by installing Java 8 across all machines. For the core software, we download the install It will download and install Apache Hadoop 3.4.2 to follow industry best practices for security and environment installation. We create a dedicated Hadoop user and group, ensuring that the Hadoop process and library file remains separate for the general system operation.
So now I'll be demonstrating how we created the log files, and I have saved the log file as this name on my desktop, and now I will open the code to show you. This is the log files. This is the Python code to generate the log files. Alright. So first of all, we have to download Python on this PC, and next what you have to do is go to the Python file location where it's saved, which is at my C drive, and we put in the file path, desktop, right? So now that we're on my desktop, all we need to do is run this Python code right here, and 1000 stands for the number of lines of logs that will be created. So I just use 1000 as a small log file to just show how it's generated, and it's going to appear here. The fake log file is going to appear here. Yeah, as you can see, it's very fast, very easy because it's only 1000 lines. So it's going to open it and show you, yep, this is how our log files are generated.
Thank you, Jun. So next, I'll be demonstrating our HDFS in action. I'll be showing two examples of our system, first with only a single node active, and second with all 5 nodes active, so that we can see the difference between single node sequential processing and multi-node parallel processing. So first, I'll have to connect to my master node. So this node is the brain of our distributed file system. It's responsible for managing resources and file metadata across the cluster. So once I'm in, I'll switch to my Hadoop user, which is a specially created user with custom environment variables. So now we can start the distributed file system using this command, start_dfs.sh. It is unable to connect to the other 4 slave nodes because I have them turned off. Now we start the yarn, our resource manager, using this command, start yarn.sh. Alright, so I already have our log file here actually stored in our master node, which is 2 gigabytes in size. So now we will have to upload this log file onto our distributed file system. So it can be uploaded using this command, hdfs. So this command basically places our log file into the input directory of our distributed file system. It is unable to place it right now because it's in safe mode, because it was unable to connect to 4 out of the 5 nodes, so we use this command to leave the safe mode for our test case. Now we try again. We upload the log file onto our file system. Okay, we can check if our log file is there. As you can see, when I list the input directory, our log file is already inside the distributed file system. So now I'll change directory to directory containing my .jar file, which is required to run the processing. So using this command, I'll take the I'll take the file in the input directory, which is our Apache weblog, and I'll place the output in the /output directory. So now the MapReduce job is starting on one node. Alright, now the file is completed, you can see how long it took. So the job started at 9:01 and it completed at about 9:05, which is roughly 4 minutes on a single node. So we can view the output. You can view the output in the file system using this ls. You can see that the job was successful, and then the output is in this file, part R000. So since the log file actually contains 10 million lines, the output file is also going to be extremely large. So we can extract this output using this command, get merge. This command will extract it. Now we have our results here in our home directory, which is for the single node processing. Since we only want to see certain parts of this filtered data, for example, the most frequent IP address, the status code distribution, and the most requested URLs, we can use these commands to filter out the results, since viewing the results.txt file line by line is extremely long. So first, I can sort out the most frequent IPs, and we can view it to see that these few IPs are our most frequent users. So next, you can see the status code distribution across the log file. So you can see that this is the overall status code distribution: 9 million status 200, 400,000 404, 400,000 301, 200,000 status code 500s. And lastly, we can see the most requested URLs using this command. We can see that the most requested URL was this /app/main/post for over 1 million requests, followed by this /list. So now that we have seen the output and our HDFS file system working, I will remove the output. And I'll remove this log file from the input. Next, I'll stop our distributed file system service and turn on our four other worker nodes. I'll also stop our resource manager. So now all of our worker nodes are active. I'll restart the command to start our file system again, and this time there should be no errors, failures connecting to slave nodes. There we go, no errors. I'll start resource manager. And now I will upload the log file onto the distributed file system again. This time it's different because the log file will be split into blocks and distributed across all 5 nodes, instead of it all being stored in just a single node just now. Okay, once we have placed our log file into the distributed file system, we can start our job. Now the job is done. You can see that I started the job at roughly 9:19 and the job completed on 9:21, roughly 2 minutes, which proves that 5 nodes is way faster than just 1 node. So you can see the output, it was a success. Similarly, I can extract this file using this command. And the output of this 5 node should be the same as when we configured it with 1 node. You can see same output for the frequent IP address, same output for the status code. And same output for the top URLs. So that's it for my demonstration. Next, I'll pass it on to Mingjun to conclude.
We successfully implement distributed log analysis performed using attached handle not release. Our primary goal was to overcome the limitation of superficial processing, which is inefficient for the massive volume of log data generated in production environment, by developing a syslog cluster within an AWS VPC. We transitioned from theoretical distributed concept to a functional real-world applications. The most significant result of our evaluation was the performance gap between single node and multi-node processing. Well, a single machine became a bottleneck, taking 4 minutes to process the log. Our distributor set out complete the task in just 1 minute. The 75% increase in efficiency proved that the log data is embarrassingly and parallelizable and perfectly suited for the MapReduce paradigm. This platform provides system administrators with a scalable solution to monitor security risks, optimize web performance, and ensure system integrity through rapid parallelized data analysis. So that's all for us.